Okay, so we have one more logarithmic equation to solve. So I have a log 5x plus log x minus 1 equals 2. And what you might notice first of all about this is that there's two logs in the problem, and you might also recognize that there's no base here. Right? One of the things that we may remember from pre-calculus is that if there's no base, there's actually an implicit base there. Okay? It's called the common logarithm. And you guys might remember that that's going to be base 10. Okay? So if there's nothing there, it's really just a base 10. One of the things that we want to do with this is we want to start by trying to get one logarithm. And you might remember that we had our rules of logarithms to where if we added two of the same bases together, it actually becomes a common base with a base 10, and we just multiply what's being operated upon. So what we can do is we can use rule number 1 from our list of properties of logarithms, and we can write this as log 5x, so I'm going to say log bracket 5x times x minus 1. And again, we're allowed to do that because, remember when we had the plus sign, that says we can multiply and turn it into one log. Okay? If it helps, just go ahead and write the 10 in there, so that way you remember that there's always going to be a base 10, it's the implicit common logarithm. Remember what we do is we turn it into an exponential sort of function. So remember, a logarithm is an exponent. Our base is 10, exponent is 2. So now we can turn this into the equation 5x quantity x minus 1 is equal to base 10 exponent squared. So at least now it's not going to be a logarithmic equation. Now it's more like a polynomial equation. I'm going to go ahead, evaluate 10 squared, and I'm going to distribute the 5 through. So by distribution and squaring, I wind up with 5x squared minus 5x equals 100. All right. Now we have a regular quadratic. Remember, to solve a quadratic equation, we have to set the equation to 0. It seems pretty easy if we subtract 100 from both sides. So I'm going to get 5x squared minus 5x minus 100 equals 0. And at this point, there's a number of ways we could solve it. We could factor it. We could use our quadratic formula. If we felt like torturing ourselves, we could complete the square. But we're not going to do that. Let's factor this. I notice that there's a common factor of 5 in all three of the terms. So let's pull the 5 out. So if I factor a 5, that really just means I'm going to divide all three of the terms by 5. So I get 5 x squared minus x minus 20 is equal to 0. Now what I notice is that I have a factorable trinomial. So now what I have to do is I have to find two numbers that multiply to be negative 20 but add up to negative 1. Okay, so when I factor this to build my x squared, it's an easy trinomial. We just have x and x. To build 20, to get a negative 1, I probably need two factors that are really close to one another. Okay? And if I go through the list of factors, I wouldn't want to pick 1 and 20. I probably wouldn't want to pick 2 and 10. I probably would want to pick 4 and 5, because 4 and 5, we know we can get a permutation so that we get a negative 1 in there. So I'm going to pick 4 and 5. To get a negative 20, we have to get one positive and one negative. Well, since we have a negative in the middle, the 5 should be negative and the 4 should be positive, so that way when we multiply it back out, we get a negative 1 to add up, but multiply to be a negative 20. So now, at this point, we use our zero factor theorem, and we set all three of the factors to 0. The first one, 5 equals 0, that doesn't make any sense. Okay? That's a contradiction. So we don't even worry about that. Okay? I always get a lot of students that ask me what happens to the 5 out front. It doesn't really contribute anything toward the solution. For the second one, x plus 4 equals 0, which means that x is going to be negative 4. And then finally, x minus 5 equals 0, or in other words, x is going to be 5. So we have two potential solutions. And I say potential because one of those solutions, or maybe both of those solutions, may not work. Because we have to remember that the domain of a logarithmic function is not all real numbers. When we took a look at exponential, we didn't have to worry about it. But with logarithmic, we do have to worry. Now, take a look at negative 4. If I substitute negative 4 back in for either of these, we would end up getting a log of a negative number. Okay, and that doesn't make any sense. So, this guy, negative 4, is not part of the solution set. Okay, because if I substitute it even back into the first expression, log of 5 times negative 4, okay, which gives me log of minus 20, okay? And we don't know what the logarithm of negative 20 is, okay? It's an imaginary number. We're not even going to look at that in our undergraduate sequence, okay? But 5 is okay, because if I substitute 5 back in, I get log of 25, okay? So this would become log of 5 times 5, which is log 25, and that's okay. We can have a positive logarithm. And if I substitute back in here, log of 5 minus 1 equals log of 4, and that's okay. So that's the way to check the answers. Substitute. If you get any negative logarithm, you stop. As long as it's positive, you keep going. And if you've exhausted all the possibilities, then it's a good solution. So the only solution to this logarithmic equation is going to be x equals 5. Okay. So hopefully, through the 3 examples we've gone through with logarithms, we've done one with just a regular log, we've done one with an ln, and then we've had one with a quadratic type. Okay. This is helpful for you guys to try to practice those last few problems that are on assignment number 2 pertaining to logarithms. The last type of equation I want to take a look at is I want to take a look at what we call trigonometric equations. And trigonometric equations are tougher because you have to do both algebraic work and trigonometric work. We're going to use our unit circle for this a lot, because this is going to help us to find all the solutions necessary. Let's start off with a really basic trig equation. Okay, so for our trig equations, a very basic example. I'm going to say, let's say 4 cos x plus the square root of 8 is equal to 0. And I want to find all the values that are going to make this true. All right. Just like we did with logarithmic, just like we did with exponential, the first thing that we want to do, we want to isolate the term that contains the trigonometric or the transcendental expression. So to do so, I'm going to subtract the square root of 8, and then I'm also going to divide by 4. So I'm going to get cos x, let's say 4 cos x, is going to be equal to the opposite of root 8. And then cos of x is going to be opposite root 8 divided by 4. Now, what we would have to do is look on the unit circle and try to figure out what angle gives us root 8 over 4. And if we look in the unit circle, we're going to be looking for a long time, because there are no root 8 over 4s. Okay, there's root 2 over 2, there's root 3 over 2, there's 1/2, etc. But there's no root 2 over 2, or root 8 over 4. But maybe we can simplify this. Remember, the square root of 8 is really the square root of 4 times 2. In other words, I just factored the 8. So what I could do is I could simplify this into 2 roots of 2. So we can say that cos x equals the opposite of 2 roots of 2 divided by 4. And again, all I did was I took the square root of 4, which is 2, and then the square root of 2 doesn't have a real nice answer, so I just left it under the square root of 2. And as you would suspect, we would go ahead and cancel these. So now what we end up with is the cos of x equals the opposite of root 2 over 2. So there are going to be some instances where you have to do some simplification to be able to get to something nice. All right, so now what we're going to do is we go back on the unit circle. Okay. The cosine function on the unit circle is the x-coordinate. Remember, cosine is the x, the sine is the y-coordinate. So the question is, where is the x-coordinate negative root 2 over 2? That's the question that we're trying to answer. At what angles is x equal to negative root 2 over 2? And I know it's difficult for me to hold up that sheet of paper for you to see, so here's what I'm going to do. I'm going to construct the unit circle, and I'm just going to go ahead and illustrate where that's true. Okay. I want you guys to look at the angle 3 pi fourths in quadrant 2, otherwise known as 135 degrees. At 3 pi fourths, the x-coordinate is negative root 2 over 2, and the y-coordinate is root 2 over 2, which we don't care about. All we care about is the x-coordinate. Okay, so this is what we're looking for. We're looking for where the x is negative root 2 over 2. So one possible solution is going to be at 3 pi fourths. And let's use the radian measure when we do this. Okay? There's one other place that this is true. Okay? Take a minute, look through the unit circle, and try to figure out the other place where the x-coordinate is negative root 2 over 2. It might just take you a moment to look through all of them. Okay? And I bet you, after a moment of looking, what you probably would find is in quadrant 3, at 5 pi fourths, you have the point negative root 2 over 2, comma negative root 2 over 2. And again, all we care about is where the x-coordinate is negative root 2 over 2. We don't care about quadrants 1 and 4 because the x is positive. Okay, so we're not looking in those two quadrants. Okay? So another solution is at 5 pi fourths. Right. Hopefully you remember from trigonometry or pre-calculus that these are only 2 of an infinite number of solutions. Okay. And why is it infinite? Because remember we have coterminal angles. Coterminal angles are the angles to where you just add 2 pi, or you add 360, same thing. So you keep adding 2 pi, you keep adding 2 pi, you keep adding 2 pi, or subtracting 2 pi. Okay? So to compensate for the idea that there's an infinite number of coterminal solutions, what we're going to do is we're going to add 2 pi times k, or 2 pi times n, whatever variable you want, to both of the angles that we found. And we state that k is an integer, meaning k is going to be 1, 2, negative 13. Just k means how many times have we traversed the circle in a 360-degree fashion. Okay? So what we're going to say is that k is an element of the integers. Okay. And this would be the solution, or the solutions, excuse me. Okay. So let's go back through really quickly, okay, before we work another problem, and see what we need to do to be able to figure out what the solution is to a trigonometric equation. First, we do some algebra, and we get the cosine, or whatever the trig function is, by itself, okay? Now that's if it's like a single cosine. If we start having like a cos squared or something like that, then we might have to do some factoring, which I'll show you an example in a few moments of that. Once we completely simplify it to the point where we get like a root 2 over 2 or a root 3 over 2 or a 0 or a 1 or a 1/2, something that's easily found on the unit circle, then we figure out what coordinate or coordinate pairs we're looking at. Since the cosine is the x, we're looking at the x for this example. And then I go on the unit circle and I try to find all the possible angles that satisfy this. Okay? And then the last thing that we do is we go through and we just go ahead and tack on the 2 pi k once we've found the angles. Okay. What you might want to do is pause here, go back and try to rework the problem without any notes. So just copy this down and see if you can rework it just from memory with the steps. Okay. So if you'd like to pause it, go ahead. I'm going to go ahead and erase and prepare another problem. Let me show you an example of maybe a quadratic type. Okay, not too difficult. Okay. Let's say I have something like 3 sine square x minus 6 is going to be equal to negative 3. And what I'd like to do is I'd like to be able to find all values that satisfy that equation. All right, just like in the previous, let's try to get the sine square function by itself and then get the sine function by itself. So obviously add 6. Obviously divide by 3. So I get sine square x equals 1. There's a couple ways you can solve it at this point. Okay? You could take the 1 to the left-hand side and factor. I'm just going to take the square root of both sides. And that's legal. Okay. Square root of sine squared, that's just sine of x. Square root of 1 is 1. And of course, we know that when we have a quadratic, there's 2 solutions. And we need to make sure that we remember that there's a plus and a minus 1. Okay. So far we've gone through and done all the algebra necessary. The rest of being able to solve this is trigonometric. Let me again draw the unit circle, and let's try to remember what we're looking for. Okay. The sine function. On the unit circle, which coordinate pair is the sine function? Is it the x, the y, or is there a ratio? Okay. Well, if you look at your unit circle, you remember that the sine is the y coordinate. So what we're looking for is we're looking for all potential values for where the y coordinate is either positive 1 or negative 1. The unit circle. Or unit ellipse in my case. Okay. Look here at pi halves. At pi halves, this is the point 0, 1. And again, all we care about is where the y coordinate is either positive 1 or negative 1. Okay? So, that's a good place to start. Okay, so that's one of our answers. So x is going to be equal to pi halves. Look on the unit circle. See if there's any other coordinate pairs where the y coordinate is either positive 1 or negative 1. And see if you can find the other one. Hopefully you went through. Okay, you're searching, and you're searching, and you're searching. And hopefully, after a little bit of work, you ended up at 3 pi halves. At 3 pi halves, the coordinate pair ends up being 0, negative 1. So now, we have that. So those are our two solutions. Okay? Not saying it's always going to be two. It is possible that we can have more than two solutions. We could have 3, 4, 5. I've even given problems to my trig class where there ended up being 7 solutions. Okay? Just 7 points within the 2 pi that's satisfied. Of course, we're going to tackle on the 2 pi k because that constitutes all the coterminal angles. And we're going to state that k is an integer. Okay? And if you leave the answer like that, that's perfectly fine for me. Okay? Another way that you might have seen the answer written, or that you might see the answer written, is notice that to get from one answer to the next answer, you're always going 180 degrees, or pi. To go from pi halves to 3 pi halves, you just add pi. To go from 3 pi halves to 5 pi halves, which would be the next coterminal angle, you add pi. From 5 pi halves to 7 pi halves, you add another pi. So another way to write the answer that you can sort of combine these together, and this is maybe how you saw it in trigonometry or pre-calculus, maybe pi halves plus pi k, okay, where k is an integer. Okay. That's just another answer, okay, a more simplified answer, just because sometimes mathematicians are lazy and they don't want to write more than one answer. Okay? Either of the two answers that I've proposed here, I'm perfectly fine with. Okay? And I think most mathematicians would understand that as well. Okay? So hopefully, again, what you might want to do is pause the video, try to work through this again. The trig ones are a little bit tougher than the algebraic ones. Algebra is a little more intuitive, even with exponential and logarithmic. Trigonometric, you have to remember that there's more stuff to do. So if you'd like to, pause. Okay. If not, let me propose one more problem. So for one last problem, let's say we have 2 sine square x plus sine x is equal to 1. Call this example C. Now, this one's going to have many more than just 2 solutions. Okay, it might have 3 or 4. All right. One thing you'll notice is that there's 2 trigonometric functions going on within this. There's a sine squared and there's a sine. So this kind of leads us to believe that it's more like a quadratic. To solve quadratics, we set to 0, right? Okay. The other one, we didn't have to do that because there was only one square. This one, we have a sine squared and a sine function. So I'm going to subtract 1. So I get 2 sine square x plus sine x minus 1 equals 0. And what we're going to do is we're going to factor this. All right. Now, I don't want you to get too scared of this. All right? Let's think of it like it's just a sine squared. All right? If I have to build 2 sine squareds of x, well, I needed 2 sine x, and then I just need a sine x. Okay? Think about that. If I multiply those 2 together, I'm going to get 2 sine squareds of x. Seems logical. To build a 1, that's easy. The only 2 numbers that are nice that multiply to be 1 are going to be 1 and 1. We need to make sure that when we're done multiplying through again, that we get a positive sign, but we multiply to get a negative 1. So since this is negative, we're going to get 1 negative and 1 positive. Okay? So here's the way I think about it. I'm going to put the positive side opposite the 2, because 2 times positive 1 is going to give me a positive 2. And I'm going to put the negative opposite the regular old sign, because that's going to give me a 1 sign. And positive 2 minus 1 sign is going to give me a positive 1 sign. All right? So this is the correct factorization. If you don't trust me, FOIL it back out and you'll see that it is. Just like any quadratic, once you factor, you're going to set each of these to 0. So I'm going to wind up with 2 sine x minus 1 equals 0. And then I'm going to end up with sine x plus 1 equals 0. Notice that we can solve both of those very easily for the sine. For the first, I would add 1 and divide by 2, so sine x is a half. For the second equation, I would subtract 1, and I would get that sine x equals minus 1. Okay? Now, unfortunately, what happens is, I get some students that stop here. Okay? But that's the algebraic stuff. Okay? And this isn't an algebra problem, this is a trig problem. So now, think to yourselves, okay, I've solved everything down. What do I do at this point? Okay? And hopefully you remember, oh, okay, well the sine is really the y coordinate. So what I need to do is I need to go into the unit circle and I need to find where the y coordinate is going to be 1/2 and I need to find where the y coordinate is going to be -1. Okay? For the last problem, this one's pretty easy. We haven't seen this one yet, but it's no big deal. Let's construct the unit circle. And you don't have to draw the unit circle or any tests or quizzes or homework. This is just so that way you guys can see where I'm getting this from. So, okay, so go to your unit circle. I'm looking for 1/2 for the y coordinate. Okay, well, I know that right here at pi 6, I have the point √3/2, comma 1/2. So that's one place that we can go ahead and get our solution for sine x equals 1/2. The other place, try to find the other place where the y coordinate's 1/2. And hopefully you look through, and you didn't have to look too far, because I believe that in quadrant number 2, our sine function's positive, and we wind up with 5 pi 6, or -√3/2, comma 1/2. So right there are two solutions for x. X is 5 pi 6, and x is pi 6. And it doesn't matter what order we put them in, it just matters that we go through and label them correctly. The last one, sine of x is -1. Again, go through your unit circle and try to figure out where the sine function is -1, or the y function is -1. And it's probably going to end up, or hopefully it ends up, at 3 pi halves, where we have the point 0, -1. Okay, so now we have 3 solutions to this problem. We have 5 pi 6, and also 3 pi halves. And of course we can't forget that we're going to add the 2 pi k to all 3 answers. And we're going to say that k is an element of the integers. So hopefully these 3 problems are helpful for you guys doing those last couple problems on assignment number 2 pertaining to trigonometric equations. All right. Let me go ahead and just list one more problem. I'm going to list it. I want you guys to pause it, try to work through this, okay? And then I'm going to work the answer with you. Last trig equation, say for item D, let's say something like cos square x minus 3 cos x equals -2. So see if you can solve that. I'll give you guys a few minutes, pause it. So hopefully you paused it, and when you come back, you were able to get at least one solution, and maybe something else didn't make sense. Okay. I'm going to assume that since you saw the last problem, you thought this was the same thing, which is good because it is. You're going to add 2 to both sides, and you're going to wind up with cos square x minus 3 cos x plus 2 equals 0. Okay. I'm hoping that you guys were able to factor this. Okay, this one actually factors a little bit easier than the previous. To build a cos squared, cos x, cos x. To build a 2, well, the only numbers that multiply nicely to give me 2 are 1 and 2. And it doesn't matter where the 1 and the 2 go. To get a positive 2, but a negative inner term, both have to be negative. Both the 1 and the 2 have to be negative. Okay? So I'm hoping that you were able to get that far with it. Okay? I'm hoping that after that, you said cos x minus 1 is 0. And then I'm hoping that you said cos x minus 2 is 0. Meaning that the cosine is going to be equal to 1. Or the cosine of x is going to be equal to 2. All right. So if you got that far, that's really good. Okay? If you didn't get that far, if you got stuck somewhere, go back. Make sure that you identify where you made your error. Make sure you don't do it again. All right. Now we look at the unit circle. Okay? And this is where some of you guys might have gotten tricked. Cos x is 1. That's easy. Remember, the cosine is the x-coordinate. So what I'm looking for is I'm looking for where the x-coordinate is either going to be 1 or the x-coordinate is going to be 2. I believe there's only one place on the unit circle where the x-coordinate is going to be 1. Okay? And it's going to be right here at 0 radians, okay, or 0 degrees. Okay? Now remember that 0 and 2 pi are the same angle. Okay? So if you said 0 and 2 pi, you're not wrong, but it's just not as simple as you could make it. Okay? At 0, this is the point 1 comma 0. So one solution that we could put in there is just 0 plus 2 pi k. Okay? So we could say x pi k, okay, which is really just the same thing as 2 pi k, isn't it? Okay? Or x is 2 pi k, where k is an integer. Okay. So that's good. So that takes care of the first one. What about the second? Well, I'm sure you guys looked through the unit circle. And some of you guys might even pull out your calculator to see, okay, can I simplify it anymore? You might remember from pre-calculus or trigonometry that the cosine function has a range. There's a highest and lowest point on the cosine curve. And you might remember that the highest point is 1, the lowest point is negative 1. What happens is that this is not part of the range, or in other words, there's no real value to where the cosine function is 2. So this does not contribute towards the solution. 2 is outside of the range.